Hello! In the previous video, I explained the concept of angular momentum and how we simulate this in a physics engine. Rotation seems simple until your engine suddenly loses a degree of freedom and your object refuses to rotate the way you expect. This problem is called gimbal lock. In this video, I'll explain why it happens, why Quaternions solve it, and why almost every modern game engine uses them. I will then show you an angular velocity implementation with Quaternions and compare its performance to the matrix implementation. Before we examine Quaternions, we need to understand what they replace and why. A point on the circumference of a circle satisfies the equation x squared plus y squared equals r squared. This relation is due to the coordinates being two-dimensional. Squaring the radius makes it equal to the combined area of the squares created with the dimensions of x and y. The ratio between the x-coordinate and the radius is called the cosine. The ratio between the y-coordinate and the radius is called the sine. The ratio between the y-coordinate and the x-coordinate is called the tangent. For every fixed ratio, there is an equivalent angle. Rotation is the continuous change of angle, which these ratios follow. Pi is the ratio of a circle's circumference to its diameter. In radians, pi represents 180 degrees. Pi divided by 180 is 1 degree expressed in radians. We use radians because they use the natural geometry of circles. They measure angle as the ratio of arc length to radius. The derivative of the sine of x is the cosine of x, but only if we use radians. If we use degrees, it would be pi divided by 180 multiplied by the cosine of x, which is not as compact. The cosine and sine functions in C++ expect the angle in radians and return the corresponding ratios. Positive rotation follows the right-hand rule. If your hand is wrapped around the axis, your thumb will point in the direction of the axis, and your fingers will be curled in the direction of rotation, which is anti-clockwise when the rotation vector is pointing towards you. The standard way of expressing rotations is with 4x4 matrices. They are used to store other transformation values such as translation, which need to occupy separate slots. The rotation values are in the upper left 3x3 submatrix. We use a matrix for rotation around each axis. The values in the rotation matrices multiply the positions of the vertices of the model. For rotation about the z-axis, the model will move in the xy plane, so the value at z on the z-row will be 1, since it will not change the position of the model along the z-axis. The same logic follows for the x and y rotation matrices. On the first row of the z rotation matrix, which corresponds to the x position, the x value is set to the cosine of the angle. Y is set to the negation of sine if you are using the right-hand rule. It's just sine otherwise. On the second row of the z-axis, the cosine and the sine positions are reversed. Sine is negated, which leaves it positive. This is because the second row is orthogonal to the first row. Orthogonality implies a 90-degree offset between vectors. You can obtain a 90 degrees rotation by negating the y value and then swapping its position with x. For the x-axis rotation, the x value on the first row is 1, following the same logic as the z-axis rotation matrix. The cosine and sine in the next two rows are in the y and z slots because we are rotating in the corresponding plane. For the y-axis rotation matrix, the sine inversions are reversed compared to the prior two. This configuration allows a positive angle rotation to move counterclockwise, which obeys the right-hand rule. To combine the rotations around the axes, we multiply the matrices together. Matrix multiplication is the computation of dot products between the row of one matrix and the column of another matrix. We do it for every individual matrix element. If you rotate one of the axes independently, you can end up with a problem called gimbal lock. This occurs when two axes become parallel, so a degree of rotational freedom is lost. For example, if the x-axis is rotated 90 degrees around the z-axis so that it aligns with the y-axis, any future attempts to rotate around the x-axis will be indistinguishable from rotation around the y-axis. One way of preventing gimbal lock is to rotate all axes simultaneously, although this would make rotation about any given axis more complex and expensive. Quaternions avoid gimbal lock by representing any rotation as a single axis and angle rather than a sequence of rotations around individual axes. A quaternion is an extension of complex numbers into 4 dimensions, a hypercomplex number. Complex numbers are comprised of an imaginary part and a real part. Imaginary numbers were created to deal with the fact that on the real number line, negative numbers don't have square roots. A negative number multiplied with itself has a positive result. The imaginary number I is defined as the square root of -1. I squared equals -1. I cubed equals I to the 4th power equals 1, completing the rotational cycle. Rotation in 2D can be expressed as a 2D coordinate system on the real imaginary number plane. Quaternions are comprised of a scalar part, S, which is often represented by the W label. This is the real part of the hypercomplex number. It is the cosine of half the rotation angle. I, J, and K are the components of a 3D vector, V, that points along the axis of rotation. These are the imaginary parts. They are scaled by the sine of half the angle. The sine-cosine correspondence derives directly from the basic complex number pair. If the scalar part used the sine and the vector part used the cosine, the identity quaternion would no longer be 1, 0, 0, 0. Instead, zero rotation would depend on the choice of rotation axis, which is nonsensical because a zero rotation has no unique axis. Multiplication of quaternions is not commutative, so a different operand order can lead to a different orientation. Multiplying quaternions adds the angles together when the rotations are about the same axis. When the quaternions are about different axes, it composes them into a single rotation. They have multiplicative properties that are superficially similar to cross products of 3D vectors. For instance, I times j is equal to k and equal to minus j times I. These equalities are known as the Hamiltonian rules. Multiplying pairs of imaginary axes leads to orthogonal results, similarly to the cross product. Unlike the cross product, quaternion multiplication is associative. Unit quaternions are required to represent pure rotations. For a unit quaternion, the inverse is its conjugate, obtained by negating the vector part. Multiplying a unit quaternion by its conjugate cancels the imaginary part and returns the identity quaternion, representing zero rotation. This is analogous to multiplying a matrix by its transpose. Imagine a vector pointing from the center of the Earth at a point on the surface. The tip of the vector represents a unique orientation on the sphere. For quaternions, the point is on a 4-dimensional hypersphere. The rotation of a vector by a quaternion is produced by the sandwich product. The vector is first embedded into a quaternion by placing it in the imaginary vector part and setting the scalar part to 0. This configuration is called a pure quaternion. The pure quaternion is then multiplied by the rotation quaternion. This generally introduces a non-zero scalar part. The result is then multiplied by the inverse of the rotation quaternion, restoring it to a pure quaternion and, in the process, canceling the scalar part. The vector part of the resulting pure quaternion is the rotated vector. For a 90-degree rotation around the z-axis, the quaternion needed is the cosine of 45 degrees on the scalar component, 0 on the x and y components of the vector, and the sine of 45 degrees on the z component. A 180-degree rotation about the z-axis is represented by a 0 scalar component and a 1 in the z component of the vector part. You might be wondering why the z component is 1 rather than the sine of 180 degrees, which is 0. This is because quaternions use half angles, so the vector part is based on the sine of 90 degrees. A 360-degree rotation about any axis is represented by -1 in the scalar component and a 0 vector. This represents the same physical orientation as a 0 rotation, even though it is a different quaternion. Only after a further 360-degree rotation, making 720 degrees in total, does the quaternion return to its identity form. A quaternion with 0 in its scalar part and 0.707 in one of its imaginary components is not a valid rotation quaternion because it does not have unit length. Normalizing it changes the component to 1, producing a valid unit quaternion representing a 180-degree rotation about that axis. Let's now look at the quaternion version of the previous video's angular velocity implementation and then what happens performance-wise. We have a constructor which can initialize a quaternion from a 3x3 rotation matrix. The next line is forward Euler integration of the quaternion differential equation. The differential equation describes the rate of change of the orientation quaternion. Angular velocity is embedded into a quaternion by setting the scalar part to 0, producing a pure quaternion. Pure quaternions allow positions and vectors to participate in quaternion operations without losing their meaning. We multiply it by the orientation quaternion, so the final quaternion is defined relative to the current orientation. The coefficient of 0.5 is due to quaternions using half angles, as was explained earlier. We normalize the quaternion to ensure unit length and then rebuild the orientation matrix from it. Note that using quaternions doesn't preclude our reliance on matrices. We still need them for the inertia tensor calculations, and ultimately transformations rely on them in vertex shaders. The quaternion implementation reduces the integration implementation from 15 lines of code to just 4 lines. This helps with readability and maintenance. We only need to normalize the 4-element quaternion rather than 3 rotation axes vectors. I used 1,000 iterations for each implementation to benchmark the performance. The quaternion implementation performs 4 times faster than the matrix version, with a minimal cycle count of 37 versus 148 and a median cycle count of 37 versus 185. The matrix implementation involves more arithmetic, including multiple cross products and multiple normalizations. The maximum cycle time was 296 versus 407. This cycle time is more influenced by uncontrollable factors, such as process switching, system interrupts, branch predictor state, cache misses, and other system noise. This is why minimum and median cycle count are better comparisons. If you'd like to help me continue producing in-depth videos on game physics and engine development, consider joining my Patreon. Your support helps me spend more time researching and creating this content. Thanks for watching.